So this is a continuation of the titration video, and we're going to go over question number 17.45 in the Brown, LeMay, Burston book. Okay, now notice here we have 1, 2, 3, 4, 5, 6 problems to do. Okay, and so what I'm going to do is I'm going to do the whole problems like I would normally, and then after that, after I do each problem, I'm gonna show you some shortcuts that I could take. Okay, but not until after I do the problem, because that's kind of, my thing. So we have a weak acid, and it's being titrated with a strong base. Okay, and so one thing, again, the book assumes that the problem assumes that you're gonna know the Ka of acetic acid, and so in this case, let me make sure that the Ka of acetic acid is equal to 1.8 times 10 to the minus 5. Okay, great, done. Okay, so now let's calculate what the pH of this solution is going to be. Now, the solution here, we're saying that 0 milliliters of sodium hydroxide has been added. So in this case, nothing has been added. Our trigger word for doing 2 steps is what we call the addition, is what I say is addition of something. So 0 milliliters means nothing has been added yet. So how do we determine the pH of any weak acid? Well, we use an equilibrium problem. Okay, so now it's just a matter of setting up an equilibrium problem. How do we set up an equilibrium problem for a weak acid? Well, we write a reaction. So the reaction is HC2H3O2 plus H2O is in equilibrium with H3O plus C2H3O2 minus. Okay. Now, what is our initial concentration of this? It's 0.15. We don't care about water. ICE. Okay, this is 0 and this is 0. Okay, so now we do minus x. Remember, because there's zeros on this side, this thing is going to, we're going to shift in this direction. So that means we're going to lose x here, and then we're going to gain x plus x. And so now this is going to be 0.15 minus x, x, x. And now we do our Ka. So that's going to be 1.8 times 10 to the minus 5 equals x, x. Every time I draw this, I always feel like I'm drawing a face, like the eyes are x'd out. Anyways, 0.15 minus x. Okay, and so now we can assume that this x is going to be small. That helps us out a little bit. Okay, let's get rid of some of those math, and now let's do some solving here. Let me make sure that my calculator is in full view. Okay, so we're going to multiply by 0.15, so 1.8 times 10 to the minus 5 times 0.15. Okay, and then so that is 2.7 times 10 to the minus 6 equals x times x is x squared. So now we're going to take the square root of that, and we get x equals 0.00164, which also happens to equal the hydronium ion concentration. Okay, well, now we do the negative log, so the pH equals the negative log of the concentration of the hydronium ion, okay, which is the negative log of this number, and so we get that the pH of this mixture is 2.78. Okay, great. That is a standard acid base, or sorry, standard weak acid problem. But now we're going to add 17.5 milliliters of sodium hydroxide. Now this creates a whole host of problems that we may not be ready for, okay? But like a good teacher, we're just going to start. Okay, so for part B, we have 17.5 milliliters of 0.15 sodium hydroxide, molar sodium hydroxide, and that's mixed with 35 milliliters of 0.15 molar HC2H3O2. Now, have we added stuff? Yes. So now in our heads, we know that we should do like a two-step problem. We're going to have to do stoichiometry, and then we're going to have to do equilibrium. Okay? So, in order to do stoichiometry, though, remember our stoichiometry step is always done in moles. So we have to convert to moles. We are in molarity here, so let's convert to moles. It just makes life easier. And this is one of those hang-ups when you're doing a titration problem that you could forget. Up until now, we haven't had to convert to moles regularly, and so now we have to. So how do we convert to moles? Well, we need this in liters, so it's 0.0175 liters. You move that decimal point over 3 spots, and that makes this liters, okay? And then I'm going to set up something that I call an X line, okay? And we want to go from liters on the bottom cancel out, to moles, and that happens to be that value, because molarity is moles per liter. So now we take 0.0175 times 0.15, and so this equals 0.002625 moles. Okay, now we do the same thing with our acetic acid. Okay, we move the decimal point over 3 spots, so we get 0.035 liters, and then I call it an X line, something from another chemistry teacher just picked it up. Okay, so we want to get rid of liters, it goes on the bottom, moles on the top. Okay, and what is the molarity? 0.15 moles for every 1 liter. Okay, so now we do 0.035 times 0.15, and so the number of moles here is 0.00525. Okay, now we can do our stoichiometry. So now with the stoichiometry, remember, always the same sort of reaction, acid plus base. Well, in this case, what's our strong component? Our strong component is the base, so that's what we're going to start with. The base, sodium hydroxide, plus, now we need an acid. Well, the only acid that we have is this one, okay? And so that's going to be HC2H3O2. Reacts to form, right, because this is our stoichiometry step, H2O plus C2H3O2 minus. Okay, so we make our ICE chart. Now, let's do it up. Ready? Okay, so do we have how many moles of sodium hydroxide we have? 0.002625. Do we have how many moles of acid we have? 0.00525. Okay, we don't have any of this, or actually water doesn't matter, and we don't have any of this. So now, because this is our stoichiometry reaction, we just find the limiting reactant and it reacts this way. Our limiting reactant happens to be this, so we lose all of it. That's the definition of a limiting reactant, 2625 minus 0.002625, and that's going to be plus 0.002625, and so now this is 0. And now we take this and subtract 0.002625. And look, we get 0.002625. And here we get 0.002625. Okay, that should be one hint that there's something kind of interesting going on here. Okay, so the fact that these are the same. Not going to tell you until the end. If you know what it is, write it down and we will go from there. But for now, we'll keep going through the problem. Okay, so now we've used up all the acid, or all the base. There's none of that left. So how do we find the pH of something like this? Well, this happens to be a weak acid. How do we find the pH of a weak acid? Well, we do equilibrium. Now, here's the crazy part, is that remember that this is in moles. So equilibrium is always done in molarity. Okay, so when we do it in molarity, we have to do moles per liter. Now, this is where it gets crazy. Well, it's not 35 milliliters, and it's not 17.5 milliliters. Because we added the two, the amount of milliliters is this plus this. So 35, and not that I need the calculator, but I'm just showing you that I didn't. So we do 52.5. So the total volume is 52.5 milliliters, which equals 0.0525 liters. So we have to make sure that we use this value for our new volume. And that's why when we do this in moles, it just makes life easier, because this step is kind of this is the new for titration step. Okay, so I'm gonna figure that out. Oh, you know what I'm gonna do? I'm gonna combine one or two steps into one here. 2 steps into one. Okay, so I need to do the equilibrium step. So the equilibrium step is going to be the weak acid HC2H3O2, because all the strong base is already used up. There's none of that left. Plus water is in equilibrium with H3O plus C2H3O2 minus. This doesn't matter. So let's go through. We'll make our ICE chart. Okay, good. How much of this do we have to begin with? Well, it's 0.002625 divided by 0.0525 liters. And so this is 0.0500 molar. And this is going to be the same because it's the same numbers, okay? 0.0500 molar. Now look at what has happened to the concentrations here. The concentrations are the same. Now maybe you remember something special about when the concentrations are the same or when the ratio is 1:1 here. Again, I'm alluding to it but not giving you the answer. But again, this is going to shift this way because there's a 0 here. So we're going to go minus x plus x plus x. And so now we get 0.0500 minus x, and 0.0500 plus x. And so we get our Ka equal to 1.8 times 10 to the minus 5, which we looked up and knew. And this is going to, from here, it's products over reactants. So products x 0.0500 plus x all over 0.0500 minus x. So now we're going to get rid of the x's. And so what's 0.5 over, or 0.05 over 0.05? Those cancel to give us 1. And so that means that x equals 1.8 times 10 to the minus 5. And so now we do the pH. So we do the negative log of the of 1.8 times 10 to the negative 5. Okay, and we get that pH equals 4.74 equals pH. Now I give you the shortcut. Okay, and many of you may have already picked up on this, but how much of this is there compared to this? It's half, right? I'll do this in a different color that way you can see it. This is half of this. Guess what part we're at? We are at the halfway point. And by definition, at the halfway point, there's a couple of definitions, okay? The halfway point means that the ratio of this to this is a 1-to-1 ratio. That gets us to the halfway point. And so because that's a 1-to-1 ratio, okay, it's a buffer with a 1-to-1 ratio, that means that x is equal to the Ka, which also means that pKa equals the pH. So all of this to say is if you recognize this as the halfway point, you don't need to go through all of this math if you don't have to. You can really just take the negative log of the Ka and get the answer. Now, how do you recognize that it's the halfway point? Well, in this problem, it's a little bit easier to tell because, look, what's the concentrations? They're the same. So the halfway point is just going to be half of the volume that's there. Now, if there's anybody writing this down, trying to figure out how the shortcut works, I will tell you that it's way easier when the volume or when the molarities are the same. If these numbers are different, it's way difficult. If it's different, this is difficult. Okay. But because these are the same, and then this is half, you can go down and you can be like, oh, it's just the halfway point. So you can save all the work and go straight to here. Okay. For my benefit, please, 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 if you're going to do this, I would please just say it's at the halfway point. Okay. Halfway point. And if you say it's at the halfway point, then we're good. Okay. Then you can go here and do that. Okay, now the next part, okay, we're already 18 minutes into this, but that's okay. The next part is at 34.5. Now, unfortunately, none of our little shortcuts are going to work here, okay, because we know that that's not half of this, nor is it equal like the next one. So 34.5 is a little bit going to be a little bit tricky, so we're going to have to go through the whole thing. So for C, okay, let's see if I can. It's going to be 35 milliliters of 0.150 molar HC2H3O2 and 34.5 milliliters of 0.15 molar NaOH. Okay, so now we want to work through the problem, okay, and we do it the same way. One of my beliefs when you're learning chemistry and how to do this is if we set up the problems the same way each time, we can build on that same way and then we can shortcut it. We don't want to shortcut it before we know the chemical principles that all of this is resting on. So, anyways, we have to do the stoichiometry step followed by the equilibrium step. So let's do that. Okay, here's the stoich, and I always label it that way. I know, okay, but the stoichiometry step is going to require us to convert this many liters, right? 35 milliliters. Okay, 0.15 moles using our X line for every 1 liter. And so when we cancel that out, we did that math earlier, Okay, and so we get, I'll just do it 0.035 times 0.15, and so we get 0.00525. Okay, so that's the number of moles. Now we have to do the same thing for sodium hydroxide, because we always do our stoichiometry step in moles, not in molarity. So it's 0.0345 liters. X line, liters on the bottom, moles on top, 0.15, because that's the molarity. 1, so 0.0345 times 0.15. And this is going to be almost that value, okay, because they're very close here. Okay, but anyways, that's equal to 0. Let me scroll this down a little bit. 0.005175. Okay, and that's moles. So now we do our stoichiometry step. We're adding, what are we adding to it? Okay, we are adding base. The base requires the acid to react with it. Okay, so then that reacts to form, because this is a neutralization reaction that goes one way, it reacts to form H2O, okay, plus C2H3O2 minus. Okay, make our ICE chart. Okay, don't care about water. So now, how many moles of hydroxide do we have? 0.005175. How many moles of this do we have? 0.00525. And then how many moles of this do we have? None yet. We don't have any yet. Okay, so now because it's the stoichiometry reaction, we find our limiting reactant. Which one is present in the least amount? Well, it's this one. Okay, so present in the least amount. So we lose this. Okay, so there's 0 left. That's the definition of a limiting reactant. Okay, and then here, because this is a product, we are going to gain 0.005175. Okay, and so now we do some math. 0.00, how many zeros? 2 zeros. 525 minus 0.005175. Okay, and so that's 7.5 times 10 to the minus 5. Okay, now this is 0.005175, and so now we have moles. So now we're ready for our equilibrium step, but remember this has to be done in molar. So we have to take this and we have to do this in this many, so because we're diluting it, so this is going to be done at 69.5 milliliters. Okay, so again, kind of kill 2 birds with 1 stone. The equilibrium reaction, this is a weak acid, so it's HC2H3O2 plus H2O is in equilibrium with H3O plus C2H3O2 minus. Great. Now what do we do? Well, same thing. We've done a million of these. Okay. Okay, so now we want to do this in molarity. So 7.5 times 10 to the minus 5 is the molarity of the weak acid. Okay, or sorry, is the number of moles of weak acid. So we have that already there in our calculator. So we're going to divide that by 0.0695. Okay, so our molarity now for this is 0.00108. Okay, we're going to do the same thing here, 0.005175 divided by make sure I run that, 0.695, okay, to get the molarity, and this is 0.075. 0.745. Okay, that's our initial amount that's going to be going through the equilibrium process. Again, notice there is no base because it's used up in the neutralization part of the reaction. So now we want this. So now this is equilibrium. So now we use x's. So this is minus x plus x plus x. So it's 0.00108 minus x, x 0.0745 plus x. Okay, so now we do 1.8 times 10 to the minus 5 equals products x 0.0745 plus x over 0.00108 minus x. Okay, a lot of work. Okay, we're only halfway done and we're 26 minutes into this video. So we get rid of the x's. So now we go, okay, 1.8 times 10 to the negative 5. Okay, so times 0.00108. Okay, divided by this, right? So 0.0745. Okay, and so we get x equals 2.61 times 10 to the minus 7. And that's also the concentration of H3O plus. And so when we do that, we get negative log of the second of that. And so we get a pH around 6.58. Okay. So now the next one is, what if we have 35 milliliters of 0.15 molar HC2H3O2 added to 35 milliliters of 0.15 molar NaOH. Okay. Some of you may understand this to be at the equivalence point. Okay. And so something interesting happens at the equivalence point that we have to calculate. So let's get into it. Okay. So okay, we approach this exactly the same as every problem. Okay, so we have to do a stoichiometry part first. Stoichiometry part means that we are going to do convert to moles. Now, I've done this twice already, so I already know that we have 0.00525 moles of HC2H3O2. I don't mind if you ever do that. If you've done the calculation, you don't have to show it to me all the time, but see, we've already done that here, okay? And now, because it's the same here, I also know that it's 0.0525 moles of hydroxide ion, of sodium hydroxide, okay? So now our stoichiometry is going to be, again, base, because we're adding the base. Bases react with the acid H3O2. Now that reacts, neutralizes to form H2O plus C2H3O2 minus. Okay. See, it's the same stuff. In my mind, it's the same stuff over and over again. Okay. When you get to that point, you know you've made it to equilibrium nirvana. Okay, so now this is 0.00525. This is 0.00525. Because these are equal in terms of their moles, that means that that this is at the equivalence point. Now, there's no shortcut like with the halfway point that you can take. At least right off the bat. Okay, so it's 0. So we subtract, because they're both limiting reactant, 0.00525. This limiting reactant is 0 minus 0.00525. That's 0. This doesn't matter, and so now this is plus 0.00525, and then this is 0.00525. Now, something interesting has happened here at the equivalence point, okay? And this is why we have to think about what's going on. At this point, we can no longer use Ka, okay? Back here, for all these other parts of the problem, we were using Ka because what was in the solution? Weak acid, okay? For part B, what was in the solution? Weak acid, okay? For this one, what was in the solution? The weak acid. Now here, what is in the solution? Is there any weak acid in this solution? No, there's 0 weak acid. What do we have? We have a weak conjugate base. So now we really need to do an equilibrium, but now it's going to be a base equilibrium. Uh-oh, life just got weird, right? Okay, but it's of the conjugate. That's fine. So what's the base? At the equivalence point, we have to flip it around, and we have to do now base equilibrium. So this is going to be the base, C2H3O2. Don't change your base reaction. You already have a base reaction, so we do the base plus water is now in equilibrium with OH minus plus, and now this donates, so this now becomes the weak acid, HC2H3O2. Okay, 32 minutes in, we're still going here. Okay, so how does this work? We don't have a Kb, but we need a Kb. We remember that Ka and Kb are related, right? Because Ka times Kb equals Kw. Oh my gosh, all this stuff we have to remember, it's all related to it, to doing these sorts of titration problems. So by doing these titration problems, you're really tackling like all of equilibrium, which is a hint for what could come up. So remember, Kw is 10 to the minus 14. Ka is 1.8 times 10 to the minus 5 times Kb. And that's going to equal that. So we do 1e negative 14 divided by 1.8 e negative 5. Okay, and so now we get that Kb equals 5.56 times 10 to the minus 10. Okay, now we can do our problem. Well, we still have to do one more thing. This was 70 milliliters of solution, 35 and 35. Okay, so 0.00525 divided by 0.070. Okay, so this is 0.075. All of this just to get to answer some silly question. Okay, now, and I have to admit, I love this. It really is a beautiful thing. Okay, but this is why the pH at the equivalence point, when you're doing a weak acid with a strong base, is above 7, because what's going to be left? There's going to be more base than anything, and look at what it's producing. It's producing hydroxide. So we don't have any of this, and we don't have any of this from the last problem. So now we're going to do minus x plus x plus x. And so now we have to go about this. Is awesome. So this is 0.075 minus x, x. So we do our Kb expression. So it's 5.56 times 10 to the minus 10 equals x over 0.075 minus x. Okay, and so now we do 5.56 5.56 times 10 to the minus 10. Okay, times, remember, because this guy can get gone, so times 0.075, and so we get that x squared equals that, so x squared equals 4.17 times 10 to the minus 11. Now we take the square root of that. Okay, and this is then, now go back to black here, so 6.46 times 10 to the minus 6 equals x. But notice now, again, because we've made it a base reaction, that's hydroxide ion. So that equals the concentration of hydroxide. Oh boy. So now we can calculate the pOH, and so that's going to equal the negative log of that value. So the pOH is equal to 5.19. So that means the pH, when you subtract, equals 8.81. Okay, but there's more, right? We want to go to a half of a milliliter over, okay? And so when we go a half a milliliter over, now we do this, okay? We're going to do the same thing. Now, if you're really good, you'd pause it and you'd work through the problem and see what you have going on. See if you can do this. 0.15 molar HC2H3O2. And at this point, I think I'm going to kind of severely shortcut some of these steps. We're 37 minutes into a video, and this is 35.5 milliliters of 0.15 molar NaOH. Okay, so we're going to do a stoichiometry. Okay, stoichiometry has to be done in moles. I'm going to write that. Okay, and now we're still adding the base, okay, plus the acid, so it's HC2H3O2, reacts to form water plus C2H3O2 minus, okay, and now we do the math, 0.0355 times 0.15, and so this is 0.005325, and now this is 0.00525, okay, and so water doesn't matter. There's none of this right now. So now notice what happens after the equivalence point. Our limiting reactant has changed. So our limiting reactant is now this. So this is minus 0.00525. And so this is 0. This is minus 0.00525. And then this is plus 0.00525. Okay, so this is 0.00525, and this is that minus 0.00525. Okay, so this is 7.5 times 10 to the minus 5. Okay. So now, is there anything that we can do here? Sure, of course we can. Okay, now we have to do our equilibrium step. And then I'm going to show you one more shortcut after this. Okay, the equilibrium step, let's keep in mind, because now what's floating around is the conjugate base and strong base, which is going to change everything in a minute. But okay, so we write a base reaction, C2H3O2 minus plus H2O, equilibrium with OH minus plus HC2H3O2. Okay, so now we go and we attack this problem. Water doesn't matter. And now keep in mind again that we have to worry about molarity, right? So this is in molarity, and it was 70.5 milliliters. So now this is 0.00525 divided by 0.0705. And so now this concentration is 0.0745 rounded up. Okay, now hydroxide concentration is 7.5 times 10 to the minus 5 divided by 0.0705. And so this is equal to 0.00106. And there's none of this. Okay. So again, we shift this way because that's what happens. So we do minus x plus x plus x. Maybe some of you math people are going to see the shortcut pretty soon, but that's fine. Okay, minus x, 0.00106 plus x, and then this is x. And so remember, we just calculated the Kb from the last one. The Kb is 5.56 times 10 to the minus 10. I'm actually getting sick and tired of hearing myself talk 41 and a half minutes into this thing. Okay, and so this is going to be 5.56 times 10 to the minus 10 equals, look, okay, so it's 0.00106 plus x times x over 0.0745 minus x. Now, ready, boop, ready, boop. Okay, so now we do some math. 5.56 times 10 to the minus 10 times 0.0745 divided by 0.00106. And so we get a value of x equal to 3.91 times 10 to the minus 8. Okay? But that is not equal to the concentration of hydroxide. The concentration of hydroxide at equilibrium is equal to this. So equals 0.00106 plus x, which equals 0.00106 plus 3.91 times 10 to the minus 8. Okay, so what is 0.00106 plus that? And notice what we get as an answer, that the concentration of hydroxide is equal to 0.00106 molar, even though we added some. So the shortcut here is after you've reached the equivalence point, once you're past it, that now, since we have the strong base in the solution, a strong base will control the pH way more than a weak base. So at this point, all we had to do back here was do the negative log of whatever the concentration of hydroxide ion that was left was. So that gives us the shortcut here. Okay, so negative log of that. Okay, that gives us a pOH of 2.97, which means we have a pH equal to 11.03. Okay, now the last one, now that we know our shortcut here, now we have, do it in black here, 35 milliliters of 0.15 molar HC2H3O2 plus 50 milliliters of 0.15 molar NaOH. And so this is way past the equivalence point, so I can use my shortcut from the last one to remember. So all we really have to do is go through the stoichiometry step, and we'll go from there. Okay. So again, our stoichiometry is always going to be what we're adding plus the weak thing. So it's the base plus the acid, HC2H3O2. It reacts to form, one-sided arrow, H2O plus C2H3O2 minus. Okay, so now do our ICE chart, do justice to this. Okay, and so now we know that this is 0.00525. That's fine, and now we're going to do 0.050 times 0.15, and so this gives us 0.0075. Water doesn't matter, that's 0. So now the limiting reactant, again, because we're past the equivalence point, is this guy. So this is minus 0.00525. So that's 0 plus 0.00525. So this is 0.00525, and now we subtract minus 0.00525, 0.0075 minus 0.00525, and so we get 0.00225. Okay, now remember the shortcut is if we have a strong component, the strong component will outweigh the weak component no matter what. So how do we find the pH of a strong component? See, that's what we did back here, is I went through and I pretended that this was a weak component and did a weak ASIM equilibrium problem. Well, the shortcut is that if you know it's a strong acid, we can just do a strong equilibrium problem. Okay, or a strong, calculating the pH of a strong acid or a strong base. So we know that POH equals the negative log of the concentration of the hydroxide ion, okay, which equals, okay, so that's negative log of that, okay, so we know that POH, oh wait, I screwed up. I was too busy zipping through. What did I forget to do? I need concentration, okay? So the concentration of that is 0.00225 moles over, now how many liters do we have? We have 85 milliliters divided by 0.085 liters. Okay, so I'm glad that I caught that because I'm sure that some of you were probably wondering what was going on. So let's 0.00225 divided by 0.085, and so now we get that the concentration of hydroxide ion, equals 0.0265 molar. And so now we do the negative log of that. Doing the negative log of that really changes that. That's the POH from my initial. So that's 1.58. So that means the pH is equal to 12.42. Okay, so there it is. Me going through this one problem took me 49 minutes, okay? I think that these sorts of problems are very good for me to assess you on whether you know how to do equilibrium, because it hits all parts of equilibrium. So your reward for actually watching all 49 minutes of this is that I will tell you that there will be a problem almost like this. I'm not going to do 6 points, but I may do 3 points, and so where you'll have to do the initial pH, the pH at the halfway point, maybe the pH at the equivalence point, okay, because that is good. or maybe maybe a fourth point where you do one afterwards. Okay, but it'll be almost like this, and I'll probably just change a couple of the numbers. Okay, so so if you've made it through, congratulations, way to go. Then don't tell anybody else in the class, because you want I want to reward the people who are watching the videos. It's good stuff. So you didn't waste this time. Okay, so have a great night and stay out of trouble.